Exponential functions. An exponential function is one of the form y equals k to the x, where k is a constant and x is the exponent or the power. So the graph of these functions are fairly distinctive. What we should know is that anything to the power of 0 equals 1. So therefore, no matter what the value of k is that we choose, whenever we have x equal to 0, we're going to have k to the 0, which means all of these graphs go through the point 1. So this graph here will cross the y-axis at 1, as will this one. They will never cross the x-axis, and hence the x-axis is an asymptote. And remember, an asymptote is a line through which the graph will get very, very close to, but will never actually meet. So let's do this example 5 and draw the graph of y equals 2 to the x. First thing we need to do is work out the coordinates. So whenever x equals minus 3, we've got 2 to the power of minus 3, which is 1 over 2 cubed. So our rules for indices, negative indices, it's 1 over the positive. So that's going to be 1 over 8, or 0.125. 2 to the minus 2 is 1 over 2 squared, which is 1 over 4, which is 0.25. 2 to the minus 1 is 1 over 2 to the 1, which is 1 over 2, so that's 0.5. 2 to the 0, well, anything to the power of 0 is 1. 2 to the power of 1 is just 2. 2 to the power of 2 is 2 squared, so that's 4. And then 2 to the power of 3 is 2 cubed, so it's 8. So we can plot these points on our graph. So when x equals 3, y is 0.125. It's going to be down here. When it's minus 2, it's 0.25. So here. When it's minus 1, we're up to 0.5. When x is 0, we're at 1. When x is 1, we're at 2. And 2 is 4, and 3 is 8. And this is the same distinctive graph as it was. And if we draw in the points with a nice smooth curve, we get the following shape. Okay, and that's what we had up above whenever we looked at this graph. Example 6, the sketch shows the part of the graph of the equation y equals pq to the x. So this is the form of an exponential because the x is the power, but unlike the previous example, which was y equals k to the x, this now has a different number multiplied in front of it as well. So we'll see that it doesn't actually go through the point 1. But what we need to do is use these 2 points to work out the values of p and q, and then use the new equation to work out the value of k when x is 1.5. So whenever we look at the first point, which was 0, 8, what we've got is that 8 is the y value, so we're going to have y, or 8 equals p q to the power of 0. And what we know is that anything to the power of 0 is 1. So q to the power of 0 is 1. So we'll have 8 equals p times 1, which is really just p. So then 8 equals p. So our equation now has become y equals 8q to the x. What we can do next is then substitute in the other points, so 118. So 18 is a y value, so it would be 18 equals 8q to the power of 1. So that's 18 equals just 8q, so q to the power of 1 is just q. And then if I divide through by 8, I get 18 over 8 equals q, and that simplifies to 9 over 4, or q equals 2.25. So now my equation is y equals 8 times 2.25 to the power of x. So if we look at our third point, which was 1.5k, and we substitute that in, we get k equals 8 times 2.25 to the power of 1.5. So k equals 8 times, now 1.5 is to the power of 3 over 2, so this is 2.25 to the power of 3 over 2, which means the square root of 2.25 cubed. Square root of 2.25 is 1.5, and then we have to cube that, and we get growth and decay. Exponential graphs represent many real-life situations, in particular situations of growth. So in exponential growth, we're thinking of things like compound interest, or we're thinking about population growth, cell division in mitosis or meiosis grows exponentially, and even all the talk about the spread of coronavirus has been an exponential growth. For things like exponential decay, we're thinking about radioactive half-life, or we might also be thinking about depreciation. Example 7 then. A culture of 800 bacteria increase at a constant rate of 14% per hour. Complete the table below. So what we need to do then is, because the increase was always per hour, that's why the table value goes up in hours. So we've got 0 hours, which is what it was initially, and then after 1 hour, after 2 hours, after 3, 4, and 5. So what we need to do is increase 800 by 14%. Now, one of the ways we can do that is by a multiplying factor. So if we've got 100% originally, and we add on 14% to that, we get 114%, which is a multiplying factor of 1.14. So to get from 800 to the next number, we'll multiply by 1.14. And we do that, we get 912. And then we'll multiply by 1.14 again. And we get 1039.7. Multiplying by 1.14 for the next hour is 1185.2. Multiplied by 1.14 gives us 1351.2, and then multiplied by 1.14 for final time to get 1540.3. So what I've done, I've just added in the scale. So I started at 800, and I've used each 10 squares is worth 200 bacteria. And then one small square is going to be worth 20. So I've plotted it 0 and 800, 1 and 912, 2 and 1039, 3 and 1185, and so on. And now I'm going to join them up with a nice smooth curve. So we've completed the table and we've drawn the graph, and then the third part of the question was to estimate how many bacteria there were after 2.5 hours. So what I'm going to do is I'm going to draw a line up from 2.5 hours to the graph, and then from the graph I'm going to draw a line across to the x-axis, and I've got a value of somewhere in and around 1100 bacteria. Example B, in an experiment, 600 grams of mass of radioactive metal decays at a constant rate of 20% per hour. So again, what we've got is that it's decaying at a rate of 20% per hour, which is why then the time is measured in hours. And because we're going up to the first 5 hours, we've got 1, 2, 3, 4, and 5. Initially, so that's whenever time is 0, we've got 600 grams, which is marked below. So what we know is that it's it's 20% per hour. So to work out the multiplying factor, so we've got 100% minus 20%, which is 80%, which is a multiplying factor of 0.8. So to get from 0 hours to 1 hours, we'll multiply by 0.8, and we'll do the same all the way along. So 600 multiplied by 0.8 is 480. Multiplied by 0.8 is 384. Multiplied by 0.8 is 307.2. Multiplied by 0.8 is 245.76. Multiplied by 0.8 is 196.608. So what I've done is I've labelled the y-axis and I've gone up in 120s. That means that each small square is worth 12. And I've plotted the points, so 0 and 600, 1 and 480, 2 and 384, 3 and 307, 4 and 245, and 5 and 196. And then I'm going to draw a nice smooth curve through each point. The last part was to use the graph to estimate how long that it takes for the half-life to decay. So what we've got is initially, at the start, there were 600 grams. For half-life, we need to see how long it takes for it to half. So if you get 600 initially, that means there's going to be 300 grams for a half. So if we go to 300 grams and read across, so 300 grams is going to be, so if we read across from 300 and follow to the curve and then drop it down, we see that we're 3.1 hours, which is going to be 3 hours and 6 minutes for the half-life.